Welcome back. This is Thermodynamics 2 homework solutions at South School of Mines and Technology. We're doing homework number 8, which is reaction equilibrium. We're doing problem number 6, which is straight out of Koretsky. It is Koretsky 9.24. Okay, so this is a nice problem. I like this problem. Why? Because it's heterogeneous. Alright. And so I've got SiCl4 as a gas plus hydrogen gas goes to Si as a solid plus 4HCl as a gas. Okay. Pressure is 100 pascals. Alright. Now, first thing I should do in every problem on these, though, is balance reaction. Now, let's balance it for you, so that's good. Okay, the reactor pressure is this. Economics dictates that you need at least 75% reutilization of CL4. That is, 75% of the silicon tetrachloride in the feed needs to end up as silica. Okay, so meaning our squiggly needs to be 0.75. Consider a stoichiometric feed of 1 mole of silica and 2 moles of this guy. Okay, so it's a stoichiometric feed. Okay. What is the minimum possible temperature in the reaction to obtain this objective? State any assumptions that you make. Well, the assumptions that we're going to make here is we're going to assume that the heat of reaction is constant with temperature. So we're going to assume that straight up. And that's really the only thing we need to assume. Oh, we're also going to assume ideal gases. We're also going to assume that the viscosity of the solid is the same as the viscosity of the solid in the reference state. Okay. So that's a lot to assume, but it's not too crazy. Okay. So I balance the reaction. That's the first thing I do. The next thing I do is I write out my reaction table. Well, let me try and erase the remnants of the last reaction table. Okay, so I have species 1, I have species 2, I have species 3, and I have species 4. Now, that species 3 doesn't really have an effect because it's solid. And so I don't really need it in things. Okay, so I'm just going to have, everything else, so to speak. Okay, so 1, 2, and 4. And I have Ni naught plus, nu I squiggly is going to equal Ni. Initial minus silicon tetrachloride, there is 1 of those. There's 2 of those, and there's none of those. Plus minus 1, nu, squiggly, plus minus 2, squiggly, plus 4, squiggly. And so I have in the end 1 minus squiggly, 2 minus 2 squiggly, and I have 4 squiggly. And then my totals are going to be 3 plus squiggly equals times nu, plus 1 times squiggly equals 3 plus squiggly. So my nu in this case is greater than 0 because it's equal to 1. Again, in the solid phase. Alright. I apologize for it not showing up very well. Okay. Now what do I do? Well, I write out my equilibrium constant. Okay. I've already written it out there, but I'll write it out again. Let's see if I can't get it. So K is equal to pi Fi over Fi naught to the nu I. Everything is an ideal gas, and so this equals N4 over N1 times N2 squared times P to the nu, which is negative 1, so over P times N total. Yeah, that's equal to K. Well, where do I get K? Well, I get K from my reaction and stuff. Alright, well, I'm going to set up the problem that way. And again, I could probably use a computer to do this. Now I want to see all the equations here. And I don't mind if you use your computer on these ones. That's fine, as long as you show all the equations. Okay, so natural log of k over k naught is equal to minus delta h naught of reaction, so we're going to assume that's constant, r over 1 over t minus 1 over t naught. Okay. Alright. And then k naught is equal to exponential of minus delta g naught of reaction over r t naught. And what's t naught in this case? It's 298.15 K, or 25 degrees Celsius. But what's delta G and delta H reaction? Delta G naught of reaction is equal to the summation of nu I delta G of formation. Now this one I have to include all the components. I have to include that solid component. Now luckily solid silica is the base form, but I still need to include it. Okay. So I have nu I of each species, whether they're vapor or not, times the delta G naught of formation of each species. And then delta H naught of reaction is equal to the summation of nu I delta H of formation of component I at standard conditions. And so what are my nu's? Well, they're right there. Plus the nu of the silica, but again, it'll be times 0, but I still want to see it. Alright. So boom, 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 you know, I plug in things, I get what I need. Okay, so what am I trying to find in this case? Oh, and where do I get my n's? Well, I get them from my table. So my n4 is squiggly, or 4 squiggly. My n1 is 1 minus squiggly. My n2 is 2 minus 2 squiggly. My n total is 3 plus squiggly. My pressure, well, my pressure's pressure. Alright. And it's saying, what's the minimum temperature? Well, it's really saying, what's the temperature so that I can get 75% conversion. So I know squiggly. Okay, so in this case, 1 minus 0.75, that's 0.25. 2 minus 2 times 0.75, that's 0.5. You know, so this is equal to 0.25. This is equal to 0.5. 4 times squiggly, so that's equal to 3. Okay, so I've got 3 divided by 0.25. So I got 12 divided by 0.5 squared, which is divided by 0.5. So really I've got 3 times 16, 48. 48 times the total, well 3 plus squiggly. 3 squiggly in this case again is 0.75. So 3.75 times 48, whatever the heck that would be. I don't even want to think about it. But I guess the total I could just add up here. 3.75. So 3.75 times 48. Whatever that would be, I don't know off the top of my head, but it would be about things so 96 48 times 48 96 130 maybe 150 something divided by the pressure. Now, do I plug in 100 for the pressure? No, I do not plug in 100 for the pressure because it's 1 bar is the standard reference state for the pressure. I have to have it in bar. I have to have it in bar. I have to have it in bar. So my pressure in this case, because it's 100 pascals, not even 100 kilopascals, it's 100 pascals, that is 0.01 bar, I think. So my pressure is really 0.01, or 0.01 if I'm, because I'm converting things in my head. But I got to make sure I got a low pressure. Okay. Why do I want such low pressure? Well, because, you know, the lower my pressure, well, who knows? Maybe the way this works is, you know, maybe a lower pressure is good in terms of how this reaction actually processes. So, but it doesn't matter. I just gotta make sure I plug in 100 pascals in bar. Okay. Part B, and then I just plug and chug and solve for T. Okay. Yeah, so I'm just solving for this one T. So, I plug that in, I get whatever, K equals that, I plug that into here, I can calculate K naught, I plug that into here, and so on and so forth. Or I just let the computer solve it for me, that's okay. But that's how you do it on a test or a homework quiz. Your supervisor tells you the temperature calculated in part A is too high. I think you get about 1000 K or something. So you suggest 2 possible strategies for decreasing the minimum reactor temperature. Indicate the effect of each of the following process changes on the minimum possible reactor temperature to attain a utilization of 75%. Well, we've already done this problem many times before, but we're going to do it again. Decrease the reactor pressure. Okay, decrease the reactor pressure, that's easy. What will happen? Well, I'm already at 100 pascals, so that's pretty crazy. But if I decrease the reactor pressure, that means this has to go up. Right? Products go up because my nu is negative. Oh wait, my nu is not negative then. My nu is positive. This is backwards. So if I decrease this pressure, the products are going to go down. That's why the pressure is so low. I want the pressure to be as low as possible because of its effect on the equilibrium constant. Okay. So that's a bad thing. Dilute the feed stream to a ratio of 1 mole of silica but 100 moles of hydrogen. So really, I'm adding hydrogen. So I'm increasing N2 squared. But I'm also increasing in total. Well, increase this, this has to increase by a ton. Okay, so yeah, I definitely want to increase how much hydrogen there is. That definitely helps me. Okay, because the nu is greater than 0, and because I'm adding products. So those are both good. And I could use my Excel sheet to find out how much it would change the temperature. Oh wait, I didn't ask about K though, did I? I asked about temperature. Or sorry, I didn't ask about extended reaction. My extended reaction is constant, isn't it? So that's not what I'm trying to find. I'm not trying to see how to make N4 bigger. I'm trying to figure out how to make K change so the temperature is lower. That's a different problem. Alright. Well, it all depends upon whether this is exothermic or endothermic. Now, within the calculations, I have to do that. Now, I think, if I remember right, that this goes down. I think this is endothermic, but let me check. Okay, so we got SiCl4 essentially, and then silica tetrachloride. Silica tetrachloride. Negative 662, that's pretty big. Hydrogen chloride. Negative 92, but times 4 is going to be negative 360 something. Okay. But it's still nothing near the negative 1600. So I've got negative 360 over here, and I got negative 600. So this is easily endothermic. Easily endothermic. Okay, so this is endothermic. So I increase the pressure. Increase the pressure, meaning K has to increase if the reaction increases. Okay. Oh, sorry, decrease the pressure. So decrease the pressure, this makes this go down. Okay, so that makes that go down. How do I make K go down if it's endothermic? If it's endothermic and I want K to go down, then I lower the temperature. Okay. Oh. Well, that's a good thing then. If I lower the pressure, that lowers the K, which makes my temperature not as high because it's endothermic. Okay. I'm increasing these guys, which makes my K go down. Is that a good thing? I just said it was a good thing. K goes down, which means temperature has to go down because it's endothermic. It doesn't. It needs a. The way to make K go down is to make temperature go down. But in this case, I'm making K go down here, so the temperature has to go down. The relationship still works. And so both of those are actually good. Why? Because nu is greater than 1.